Welcome, everybody, to the American Space Museum. I'm Marquette, and we're so glad you're with us to stay curious. Today we have astronomer Eric Pearlman with us. Welcome, Eric.
Thank you, Mark.
How'd you find? You didn't get a chance to look around the museum yet. He just kind of crashed into our place here. And we're going to have a great conversation about black holes because we got the Hubble Telescope behind us here, Eric, that you have done research work with. This mighty instrument, one of the greatest things ever made by mankind. And he is going to work on the Webb Telescope and tell us about how he's excited about watching it unfurl and when can we expect his science to start coming from there. But Eric, thank you for being here. We want to let our friends know that oral histories like these are made possible by the Marie Louise G West Endowment that gave us some money to buy the equipment we needed to Stay Curious to another level here. And we've got people watching us, Eric, all over the world on Facebook, YouTube. We got Robert Laws having his cocktail on his big TV screen in Dundee, Scotland right now. You're going to enjoy this conversation, Robert, about black holes with a man that is an expert in them because he's making a living at it. But we hope you enjoy us on YouTube, Twitch. We're also on Spotify video, and we're on audio, Apple and Google, all thanks to our Trekkie techie Jessica Galloway. She's off, not in our studios here in downtown Titusville in the American Space Museum, but she helped Marty Winkle, my buddy behind the camera, and the console there get us started today. So we got Eric Pearlman here. He's an astronomer. He promises not to talk over anybody's head. We got some pretty pictures to show you. We couldn't get loaded up all the stuff that he wanted today, but we're going to have Eric back many times as part of our museum and our go-to guy. Eric, tell us a little bit about yourself. Where'd you grow up? How'd you get involved in astronomy?
So I grew up in Phoenix, Arizona, and
You're good. You're good. Yeah.
Okay, I grew up in Phoenix, Arizona, and I grew up basically looking at the stars in my backyard. I'd sit out there, at first just doing that with my naked eye, and then my mom and dad gave me a pair of binoculars. And so I'd sit out there and I'd be looking at the stars. You know, I'd go from the Orion Nebula to Jupiter to, to the Ring Nebula, to basically whatever else was out there. And, just love to watch the stars at night. And that's how I got my start.
With binoculars.
With binoculars,
Because we talk on our Monday, Star Curious with Stay Curious. We did an episode you can see. I talk about binoculars all the time. That binoculars are a great way to get started, and
that's exactly how I got started.
Neat. So, how'd you get wanting to be an astronomer?
So, yeah, I went from there to reading books. I was always a big reader, and so I started reading books on astronomy and lots of science fiction. So, Isaac Asimov and books about galaxies and books about the planets. And it just sort of grew into that. It just, it became the thing that I wanted to do. And I was always the kind of person who, once I made my mind up, you couldn't change my mind. If it was something that I really wanted, then I just had to do it.
Mm-hmm.
So that's how I got started.
A lot of astronomy people are like that. Of course, our Stay Curious fans know that I'm an amateur astronomer all my life. I tease and say, how can someone know so much about something for 60 years and still be an amateur? All right. When you're making the big money,
not that big money.
Not that big money. Right. It's sort of the liberal arts. I tell kids, like I went to, go be an engineer if you want to make some money. Okay, liberal arts, the cream of the crop makes some good money, but But no, it's a passion that everyone has. You kind of get hooked on the stars. I don't know where it came from with my case, Eric, but no one else in my family has even got a vague interest in astronomy. Is that the same with your family?
Well, except for my older daughter.
Uh-huh.
My older daughter, so she's not interested so much in stars, but she's interested in other planets.
Mm-hmm.
And it's fun, you know. I'm watching her. She's 19 right now, so she's in her sophomore year.
Elenia. Hi, Elenia.
Eliana.
Eliana. Okay. I tried. And Rachel's your other daughter,
That's
who's
right.
16.
That's right.
All right.
That's
Well, they'll
right.
be sharing this with all their friends to embarrass Dad, I'm sure, in the next couple days here. Yeah, you can't always have kids following your own footsteps, but it's nice when they
exactly
have
right.
some of the interests in you.
Oh, yeah.
On there. We're talking here with Eric Pearlman, and I want to set this up that he is at the Florida Institute of Technology. It's just about 40 miles down the road south of us here in Melbourne. And it's a great, speak of the Florida Institute of Technology there. For people out there that don't know it, it's an up-and-coming engineering school
Right.
with a lot of science.
That's exactly right. So Florida Tech was born out of the space program. We started in 1958. So, you know, right after Sputnik went up, we were the place that missilemen came basically to learn what they needed to learn to launch rockets, to put together space missions, to build things in space. This is where we did that. So we actually started as a graduate school because we didn't have undergraduates for several years. We basically just had people who wanted to go into careers at Kennedy, you know, and they came out here, right? And space was a brand new thing, right? So we barely knew how to get stuff beyond the atmosphere. We had to learn to get stuff A, beyond the atmosphere, B, into orbit, right? And then C, further than that. So Florida Tech was part of that from the very beginning. And so because of that, science and engineering have always been the things that we specialized in. And we're kind of a small to mid-sized school. We have 6,000 students, and about 2/3 of them are in science and engineering of one sort or another. My department, which is aerospace physics and space sciences, sort of combines the two historical places where the university really began, because, you know, aerospace, learning how to fly stuff, and the physics of actually getting into space, and then obviously space sciences. And I kind of sit in the middle between physics and space sciences because I do a lot of both.
This man has been a frequent user of the Hubble Telescope behind us here, the Chandra X-ray Telescope. I'm sure the Gamma Ray Observatory might be in your wheelhouse too. A little bit in there. Any orbiting telescope here, Eric's familiar with there.
Pretty much.
Then, and to kind of button up the Florida Institute of Technology there, Buzz Aldrin had office there for a while, did he not?
Yes, he
His
did.
son's very involved. Is it Mark Aldrin? Or which Aldrin's is involved there? But Marty, Marty knows the George Skurla building there. Skurla being the gentleman that managed all the Grumman workers
right.
here.
That's
Marty
right.
was a lunar module electrical engineer, was in every ascent stage, looking out them triangular windows once in a while, doing his job.
All right.
Either at the Kennedy Space Center or 340 feet high. He was actually up there inside the slaw working on that thing. 320? 320, okay.
Okay.
In there, 320 feet up there. And FIT had a wonderful, 2 winters ago, a wonderful Apollo 50th anniversary event there, and that was one of Al Warden's last events that he was in public there, and I got to see Uncle Al there, so that was a great event that you guys put on there. And of course, friend of our museum, Dr. Winston Scott, is an advisor to the president there. and a good guy to see walk around your halls, I'm sure.
Oh yeah. Oh yeah.
Mr. Well there. So that's given Dr. Perlman here his egghead status, if you will, that he's qualified to talk about what he's going to talk about there. And what we're all going to talk about is a little bit about the Webb Telescope, but also to excite you about the rare things, the exotic things. And he's going to talk today about the black holes. We'll have him back to talk about some other things. But Dr. Perlman, I say this a lot. Science fiction cannot even get as crazy as real science fact.
It's very true. It's very true.
And no more crazier things than black holes and what we've learned about them the last 30 years, thanks to astronomers like yourself. So let's look at how science fact is crazier than science fiction. Let's first start off here with the deployment. Did you have your toes crossed while this was going on, as well as your fingers? How was
my God,
an
yes.
actual astronomer that's going to work on this? How did you feel about that tense week of unfurling this beauty?
I was very nervous, and I made sure that so day by day, when one thing more was deployed, I was checking up on it, and I was listening to NASA TV. Got up early for the launch, and basically until all of the stages were released, I was nervous throughout that. I was very nervous on the days that they were deploying the sun shield, and then the two wings of the mirror also made me nervous. There were so many things that could go wrong. There still are things that can go wrong. It's not that there are single point failures. We're past the last single point failure. So at this point, we know that it's going to work. We just don't know how well it's going to work.
It's going to gather light. It's going to go to that boom that's out there extended. That's the secondary mirror to shoot the light back to all those science experiments.
That's right.
Some of them are buried underneath the sun shield. But so that's good news. Tell us, what are they doing now and when will you start doing some science on it, Dr. Perlman?
Right. So what they're doing now is that they are, well, first of all, it's in the process of beginning to change course to enter orbit around L2. So it actually inserts into L2
the
orbit.
Lagrange 2 point.
That's
a
right.
Point in space 1 million miles away.
That's right.
Nothing to do with Lagrange and ZZ Top, though we like to think so.
There's a lot of ZZ Top playing in observatories sometimes.
I'll bet there is.
But seriously, the actual burns have been going on since about the third day. So there's been 4 different burns to correct the course a little bit during the last couple of weeks. And basically they're to adjust the course a little bit so that we can nudge it into orbit around L2. The actual insertion into L2 orbit happens next week.
Okay.
And we're the other thing that's going on is that, so we're waiting for everything to cool down. So once the sun shield was deployed, all of the telescope's optics and particularly the instruments, they started cooling down. They're designed to operate at temperatures around 400 degrees below zero.
That's cooling down, folks. 400 below zero.
That's exactly right.
Yeah.
It takes a lot of time to cool down and then just come to a stable equilibrium at those temperatures. That's the other thing. You want to have a stable temperature as well as a low temperature, right?
And to analogy of that, Eric Pearlman, would be you don't want any heat lines like on a road. You see the mirage of the heat going on there. Astronomers are always trying to cool their telescopes down there.
That's right.
And but there's a lot of technical things about this. We'll have you back when you're doing science on this, but when is it 6 months that you might be able to start working with stuff, you think?
That's exactly right. So 6 months, and there's
So
various.
sometimes late summer we'll be seeing some data from
That's
this.
right. And in fact, if you can put up that next graphic, there we go. And this is the timeline for basically the next 6 months. So you can see that we're right now just a few days before arrival at L2. And what you can see there is that the next 6 months is chock full of basically calibration of every instrument and making sure this works and making sure that, every single day is going to be full of making sure it works. And I think the most critical thing that we haven't checked out yet is that we haven't checked out the focusing. That actually is something that a lot of people are nervous about. I'm a little nervous about it myself because so it wasn't launched in focus. And that is because if you launch something in focus at room temperature, it's not going to be in focus at 400 degrees below zero. And remember, too, the main mirror is not on the cool side, right? The secondary mirror isn't on the cool side. But then all of the optics are on the cold side of the mirror. So that all has to be accounted for, and you can't account for it until everything is in space and in its equilibrium, and that's why the checkout time takes this long. And I don't know if you remember, but when Hubble was launched, it had a several month long checkout phase as well, and so did the Chandra
any
X-ray
instrument
telescope.
does. Any
That's right.
weather satellites and so forth, they have to go through
That's exactly right.
a little process there. So where is the headquarters for this? So you say check out. Where are these people checking it out at? Where's their consoles at?
So the people that are working on it are in Baltimore.
Okay.
At the Space Telescope Science Institute, where I used to work.
Where the Hubble is run. So it's the same group of people or a different group of people?
So it is some of the same people, because what happened is that several of the people who worked on the Hubble moved over to work on Webb, and there's also new people as well.
Okay.
So it's a combination.
Okay. One interesting thing being in academia is if this thing doesn't work, then a whole bunch of people counting on having a job for the next 10 years aren't going to be doing with the Webb, right?
Right, exactly.
I mean, you can't believe the amount of careers that are on the line and how many careers the Hubble has made because it lasted longer than we thought it would. We thought it was going to last at least 20 years, and it's in its 30s, coming up on 32 years here in April.
That's right. And it's evolved from being something that we looked forward to then in the first couple of years kind of being a joke because it wasn't working properly.
Right.
And when I was in grad school, we called it the Hubble Space Telescope because
Hubble Space
because
Telescope,
it wasn't working properly. And then the mission that fixed it was in my third year of grad school. No, fourth year of grad school, excuse me. And then it basically became what launched my own career because my time at the Space Telescope Science Institute, that was 4 years of using Hubble. It was 4 years that basically transformed what I worked on, and I came out of it, a much better scientist.
Interesting. We're talking with Dr. Eric Perlman from Florida Institute of Technology. He's an astrophysicist there, involved in teaching kids the raw science of physics of astrophysics, as well as his specialty in black holes. Looks like we've got a bunch of your students maybe looking for extra credit here. We've got Anastasia Zanetsky, Karen Matarala. She says, "Go Panthers."
I know
Is that
Karen. Yeah.
All right.
That's our mascot.
That's your
yeah.
mascot. Melisandra Widener, Zeljaka Misajek. That's a hard one to pronounce.
I'm not sure who that is.
And we've got Madeline van der Laan.
Okay.
And Laura Mendez. Laura Mendez. Thank you all for watching and staying curious, and tell your friends. If you are students of Dr. Perlman here, I'll send a note home with him to give you a gold star there. All right.
There you go.
We appreciate that. We've not had a lot of time to talk, and we're really looking forward to you being partners with our American Space Museum and being our go-to astronomy guy. But I gather that you've been on top of every major observatory in the world, like in Chile and Venezuela and so forth. Am I wrong about that, or no? You've been
not to every single one, but I've been to a lot of them. I've been
Mauna Kea, of course,
Mauna Kea several times. I've been to five of the Chile. Five of the mountains in Chile, but not every single telescope.
Mm-hmm.
I have been to Palomar. I've been to Lick. I've been to the Very Large Array. Used it many times.
Oh wow, Very Large Array is pretty cool.
Yeah, it is. It is.
And that was part of the movie Contact. Those of you out there,
that's exactly
Jodie
right.
Foster.
Yeah.
So being naive, and for all you stay curious people out there, and I'm sure Dr. Perlman will agree, there's really no silly questions in astronomy, though we get a lot of silly questions, okay? Why do we put observatories on top of these hard-to-get-to mountains with these gigantic structures up there, Dr. Perlman?
So basically we put them there because we want as little light pollution as possible. So we want them to be as far away from cities as they can be, so that the skies are as dark as they can possibly be.
Mm-hmm.
We also want a dry environment. So almost all of the telescopes are in some kind of desert.
Mm-hmm. Humidity's not good for optics because there's moisture in the air that refracts light.
That's right. And humidity is particularly not good for anything in the infrared, because if you're looking in the infrared, there's all kinds of different lines from water and from all of the other molecules. And, we can't have that if we're going to do any serious work. Mauna Kea is the only one that's not in a desert,
Arid,
but it's 14,000 feet.
Mm-hmm.
And so what saves it is that cloud deck, that basically holds in all the moisture at lower altitudes.
This is not an exotic lifestyle, is it, Dr. Perlman? You're kind of in you're up all night. Actually, your data is being collected. Briefly tell us, you don't look through these telescopes, through the eyepiece, right?
No.
Tell people, and usually there's a bunk bed or something like that. Here's your room here. Okay.
That's pretty much right. So
you're looking like FIT could have spent a little more money and got me a better room up here, couldn't they have? I don't know.
So you if you go to a professional observatory, so your first stop, you obviously you have to check in, and you stay in a dormitory, okay? And the dormitory is not always at the top of the mountain. At Mauna Kea, for example, it's about halfway up. And the reason it's halfway up is because you don't sleep well at 14,000 feet.
I was going to ask you how you acclimate to the thinner air.
So some people acclimate more easily than others. I acclimate pretty easily, but other people have a lot of difficulty with it. You need a day or two.
Mm-hmm.
And
sleep's affected, you say, by the
sleep
whole
is
thing.
definitely affected. I mean, more in some people than in others. I went to grad school at Colorado, so I think it's a real thing that my body has a memory of what it was like to live a mile high, right? And so I think that probably has affected how well I acclimate to altitude. I don't have a problem with it. Let me kill my phone.
Well, I'm fine as much. We're going to get to some black holes and some raw astronomy here, but I enjoy talking about being an astronomer and kind of demystifying for that out there. I'm sure Melissa Pope is enjoying that. Space Coast Office of Tourism. We've got Christopher Mick. I'm sure you're eating all this up in Hudson, Wisconsin. He's a STEAM educator.
Oh, okay.
There. We've got Larry Puskers in Sterling Heights, Michigan, freezing his patootie off up there, I'm sure. There. And Dan Vranick is an amateur astronomer, does some great astrophotography in Fort Wayne, Indiana. Hope Dan Vranick's enjoying this. So, pardon me? Keith Sowell. Hey, Keith. Keith's a local astronomer teaching at the community college.
Okay.
Here.
Not a community college.
Who?
It's not a community college.
Florida.
Florida.
What? The Florida.
East Florida State.
East
Oh,
Florida
East Florida
State.
State,
East
yeah.
Florida State.
Yeah.
Not a community college. I'm sorry.
That's
there.
right. They
East-
haven't been a community college for a few
East
years.
Florida State there.
That's right.
And Keith is teaching an astronomy class up there on there. Let's talk a little bit. A couple other things about the Webb here. Tell us what this picture is all about.
So this is a picture taken on launch day, but a few hours after launch. And what you're watching there is at the top, you've got the Webb Telescope heading out to L2, and then further down at the bottom,
Near the steeple.
you've got Comet Leonard.
Okay.
And it's just a beautiful, superposition of those two.
Yeah, there's Comet Leonard. We
That's
talked
right.
about that. I never really saw it very good or photographed it. I didn't get to a dark
Neither
area.
did I. But I'll tell you, one of my best memories of being in an observatory was about 25 years ago. It was
Hyakutake.
Yakutaki, and I was in Chile, and
wow.
I was at the observatory. It was 2:00 in the morning, and I was doing my observation. And as so often happens, you set your observations going, and you've got a loop that runs for like an hour. So you step out and you look up at the sky. And sometimes you're looking at weather, and sometimes you're looking at the stars. And that particular night, I was looking at Comet Yakutaki, and oh my God! I mean, it was bright. It was right in front of the Milky Way, and it was gorgeous.
That was the one before Hale Bopp. Hale Bopp was 86 and 96. In 95 was Hyakutake.
Mm-hmm.
We had two good ones back to back there. You were saying looking at a run. Explain what you meant by a run there. When you're up on the observatory,
Right.
you've got a project in mind. You're looking at one certain black hole. We're going to get to the black holes here.
That's right. So when you go up to an observatory, you've written a proposal and you've gotten a certain number of nights, right? And so you don't go for one night. You go for 2, 3, 4, 5, 6 nights, right? So, and they're usually all in a row, one right after the other, after the other, after the other.
Mm-hmm.
So we call that an observing run. And so, you might be lining up a bunch of black holes. You might be lining up a bunch of galaxy clusters, a bunch of stars to observe. It might be anything like that.
Mm-hmm.
But, you've got different objects on different nights. You've got different objectives on each night. And so it's a really, you've got to be on your feet because you've got to respond to conditions because, if clouds roll in, you have to change your program or you have to stop observing if you can't observe anymore. You've got to make decisions on your feet because you never know exactly what the conditions are going to be until you get there.
Oh. Well, let's talk about one other thing that popped into my head because talking to Eric Pearlman here, he's been on all the major mountains of the world that have observatories doing raw science and astronomy. Then you get that raw science, and you spend probably months analyzing
That's
it back
true.
at home, right?
That's right.
But today at 7:04, we're going to add another 50-some Starlink satellites to that constellation up there. As I see you roll your eyes, tell the common our stay curious people out there, Joe and Jane America,
Right.
what an astronomer like you feels about these. They can go through your data and
That's
match your
right.
data up. So
That's
give,
right.
give me the your opinion of that.
So, my opinion of it and my problem with it really is that Starlink satellites basically they mess up your data quite a bit. What they do is they literally streak through an image taken by a telescope in a matter of seconds, and they're really bright. So what you have is you've been taking this picture, right? You've been exposing for 30, 40 minutes. But in just that 30 seconds that the Starlink satellite streaks through your field, it's brighter by a factor of 1,000 than anything that you're looking at.
Wow.
And it has left a streak going through your field, and it wipes out everything that was underneath it. So automatically you have a streak, a couple pixels, maybe 5 pixels wide at most, but it stretches from end to end of your image. And if you have an hour's exposure, you very often now have 2, 3, 4, 5 of these. And you don't know where they're going to be, where they're going to appear. You don't know what's underneath them. And you don't know what it was doing, right? That might be your object of interest, or it might not. You don't know. And in many cases, one of the things that you're doing is that you don't just have one object of interest, right? Let's say you're looking at a cluster of galaxies, right? And so there's not just one object of interest. That cluster has 1,000 galaxies, right? And you're taking spectra of 100 of them. And any one of those 100 could be, in that path, could be compromised. So that is the problem that an astronomer like me has with the Starlink satellites. And I mean, what we really want is we want two things. We would like to have a database that tells us where they're going to be so that we can know to avoid them. But the problem is that they're in so many places that what we really need is we need this in a computerized form so that the computers that run the telescopes can basically build their exposures around it. And then we need them to actually be a lot less reflective than they are. I mean, that's the other problem. The reason that they're so bright is because they're reflecting the sun's light. And, they're so bright that they just, they burn out everything.
Well, it's a problem, and with 2,000 orbiting right now, and another possibly 10,000. Is there really a solution, you think?
So I think there is, and I just wish that the conversation between Elon Musk and astronomers on that subject would have started earlier, because I think that a lot of the problems were to some degree avoidable.
Okay.
And
in the hardware, building it and so forth, maybe.
yeah,
Okay.
I think that conversation should have gone on years before, and that it's something that we should have been privy to, because the
Absolutely.
fact that we were affected, that should have been something that was anticipated.
Can you give me a round figure of what it costs FIT to send you to Sierra Tololo, for example, for a run?
Right. So
This is what I'm getting at, is it's a financial
right.
loss to the university sending good people like him to get their data, and then the data is wiped out. So is it $100,000?
It's not $100,000.
Okay.
It's I mean, so the financial cost of actually sending somebody, typically you send two people on an observing run, and having two people is just really important because you cover for each other in the middle of the night. You're tired, right? And so having two people is just so important because you cover for each other and you're able to do more things, and it's just a good thing. So you take two people and you figure in airfare, and you figure in you figure in room and board. It's about $6,000 to send two people on an observing run. But that's not the problem. The problem is that if you think about what time on a major telescope actually costs in terms of the operation and in terms of the manpower, then you're talking about depending on the telescope and amortizing the cost of building it and operating it over years. So for a 4-meter class telescope, it's about $20,000 per night. For a 10-meter like the Keck's, $50,000 or $100,000 per night. And so, then you're talking about some major change because, let's say you've lost half of your data over a 4-night run, just say, right? Well, then, that's half of, say, $400,000 that's down the drain, right? It's not so much the cost of sending me and my graduate students.
It's reserving the time on the
It's the
telescope that the
time-
university's paying for.
Exactly.
Huh.
Exactly.
Well, we've got a question here that I said Eric doesn't look through an eyepiece in the telescope, so why go to an observatory?
Well, so that's actually a very good question, because now with the internet, you don't necessarily have to go to the telescope. And so a lot of the time when you observe now, what you do is you get a request for a command file. And that command file it's a series of commands: point to this target with this instrument and do it for this length of time, and then go to this target and then do that and do this. And so it's a whole list of commands that lasts for the entire length of your observing run, and you can do it while sitting in your living room. And the operators take the data and they put it onto the internet, or they send you a CD perhaps, and then you get it. Then you get it over the internet. We have a network of telescopes. SARA, the Southeastern Association for Research in Astronomy, has 3 telescopes that we operate: one on Kitt Peak, one on Cerro Tololo, and then the third one on La Palma in the Spanish Virgin Islands, and that's not Virgin Islands, Canary Islands. And then we're sitting in, we have 2 labs that have operating computers at FIT. We're sitting in those, but we're remotely operating the telescopes. And so nowadays you don't need to, but go back 15, 20 years, you absolutely needed to be at the telescope because the internet wasn't there. Right. And so you had to be there with the operator. And the other thing is that, there was no other way to schedule it, right? Because you had made a proposal for, science XYZ, and the other person had made a proposal for this science, and then the third we all had our agendas, right? and we all made our proposals, and we got our time. Well, you want to be there, right?
Mm-hmm.
You took the time to write the proposal, and you physically want to be there. It is a personal satisfaction kind of thing to be there at the telescope, right?
Mm-hmm.
And to see your science being done with the telescope. I mean, every astronomer that I know, every professional astronomer that I know, takes pride in what they do, and it's fun being there at the telescope, and it's fun doing it in real time. It's not quite as much fun sending the command file,
Mm-hmm.
and then when Hubble observes my targets, I don't have to be doing anything at the time, right? I've sent it my command file, and it just executes it, right?
Mm-hmm.
And it might execute part A on December 28th, and part B on January 5th, and part C in March,
Mm-hmm.
because they have computers that just sequence the whole thing, and they try to build the most efficient schedule that they can. But there's a little bit of something lost, because then I get an email, right? And it says, oh, your observations have been taken today, right? And the data is going to be available in a couple of days. And in fact, this just happened to be, what was it? Over the weekend, with some observations from the Chandra X-ray Telescope.
Mm-hmm.
And so I got the notification on Thursday that my observations were going to be occurring over the weekend.
Mm-hmm.
And they occurred on Saturday. And then, Monday, I got I got a first look at the data, right? They sent me a JPEG, said this is what a JPEG of your field looks like. And that's good, because then oh, this is what it's supposed to look like, right? My target is right there, and it looks like everything worked pretty well. And then a day or two later, you can download the data. It's available by FTP.
Yeah, wow, that is interesting. How many astronomers, professional, are in the world?
So I don't have the list throughout the world. I do know that if you look at the American Astronomical Society, which is the U.S.'s association for professional astronomers, that's about 10,000 members.
10,000. Wow. I wanted to emphasize it's a low number.
Right.
Okay.
Right.
There might be 1 million amateur astronomers in the whole world. It's really, sometimes I don't see how they can make the equipment and sell it, because when you got like 10 million people are members of Bass America Fishing.
Right, exactly.
In there. It's in there. What do you think we'll see? Larry Pusker's got a question here. And we thank your questions, and really thank you talking to us about astronomer. We didn't really talk about this. We've gone 40 minutes, and I do want to get into the black holes here a little bit.
Okay.
But what do you think we will see with the Webb that will totally surprise the world, says Larry Pusker.
Oh boy, I think we're going to see a whole bunch of things that will totally surprise us, because we're going to be looking further back in time than we've ever looked before. And the reason why is not only because it's a bigger telescope, which it is, but because we're looking in the infrared.
Mm-hmm.
And so because we're looking in the infrared, we're looking to light that, it was emitted in the optical, by the stars and by the galaxies very, very far away, but it's shifted into the infrared. And that's what makes Webb so unique, is that it's an infrared telescope. So what could we see that would be different? We are going to learn about what the first stars were like. We're going to learn about what the first galaxies were like. Did black holes form at the same time as the galaxies that hold them are, right? We know that there is a black hole in basically every massive galaxy at its center. Well, which one formed first? Did the black hole get there first and the galaxy form around it? Or did the galaxy form and then later some of the mass clump together and form the black hole? Right now, we have black holes that are there as far back as we see galaxies. Well, that's great, but at some point, one of those things had to be there first, right? We don't know the answer to it.
Which came first, the chicken or the egg,
exactly
right?
That's
in a
exactly
cosmic
right.
scale. Well, let's look at some black holes here. I know we've got 40 minutes with Dr. Eric Pearlman here, and I hope you don't mind sharing. We got off that tangent of what an amateur astronomer is, and fascinated with that. But let's in 10 minutes or so go through here the kind of 101 of a black hole and why they're so important.
Right. And so you're looking there at sort of the anatomy of a black hole. And a black hole, just to step back, a black hole is something that's so dense that even light itself can't escape from it. So its escape velocity is faster than the speed of light. Nothing can go faster than the speed of light. So that black circle at the center, it's labeled a singularity, but the black hole is inside of that, right? We don't know where its actual surface is. We don't even know if it has a surface. What we do know is that there's this huge amount of mass that's in there, inside that singularity, right? And the outer border is the event horizon. And then what the Event Horizon Telescope saw in M87, and do we have a picture of that?
I don't think so.
Okay, no, this is fine. So what the Event Horizon Telescope saw, and many of you may have seen this this sort of visualization if you saw the movie Interstellar.
Right.
Okay. These visualizations. That's exactly right. So these visualizations were built at Caltech by Kip Thorne, and they accompanied the movie, and they were used in the movie. Okay. And what we saw in with the Event Horizon was the photon ring. So what's the photon ring? 1.5 times the radius of the Event Horizon. You have light being able to orbit the black hole, and it goes in it is a straight path, but because of the warping of space-time, it's actually orbiting the black hole.
So that's what this is demonstrating.
That's exactly right. Those are those rings around the black hole. And then further out, there we go. So further out, what you have is you have the accretion disk. So this is matter that's orbiting the black hole.
Right above my head here, towards the accretion disk.
Exactly. This is matter that is orbiting the black hole, and it's slowly moving in, right? And it's really, really hot. Slowly moving in, and then eventually accreting onto the black hole. And the that is the material that we see not only around, but also because of the warping of space-time, we see it behind the black hole as well because of gravitational lensing. And we can even tell which material is going in our direction. So that material is orbiting the black hole, right? Well, part of the ring is approaching us, right? Mm-hmm. And part of the ring is going away. If you look at the brightest part of the ring, that is actually what we call Doppler beam. Now, what Doppler beaming
on the
is
left side up there.
That's exactly right. The material on the left side is material that is going around the black hole at a fair fraction of the speed of light. How large of a fraction? So if you're at the innermost stable orbit, which is the innermost part of the accretion disk, that material is orbiting the black hole at about 40% of the speed of light. And so it is quite a bit brighter than the material that's on the other side.
Above your head there.
Right, that's going away from us. So
you see that arc again, that is a gravitational lens where the accretion disk behind the black hole, the light is being gravitationally lensed and thrown up so we can see it, as of the bottom. That's why it looks like that, instead of like the ring of Saturn.
Well,
the back side of it is
well,
being shown.
and in fact, what you're looking at there, you're looking, so the backside, the stuff that appears to be above the black hole, that's actually the far side of the disk. And then you can actually see, again, because of the lensing of light, you can see the underside of the disk as well. That's the stuff under the singularity.
And Webb's going to see this something like
so
that.
Webb isn't going to see that. That's what the Event Horizon Telescope is seeing. What Webb is going to see, and it's going to have to work with the next generation of X-ray telescopes to do this. Webb is going to see the very first generation of these black holes appear. When do they appear? Right? And yeah, here you can.
Here we talk the gravitational lensing.
This is the gravitational lensing around black holes.
Predicted by Einstein
exactly.
in the early 1900s.
Exactly. Now, some of the other things it's going to see, Webb is also able to look at planets around other stars. I mean, planets around other stars are also brighter in the infrared because, they're not as hot as their stars, right? They are at much cooler temperatures, but their stars are fainter. So we'll be able to see planets around other stars, and we'll be able to take spectra so we can know what's in their atmospheres. And here's one of the things that I think that I'm going to be surprised by. We don't know how likely life is in the universe. I've gotten more and more interested as I go on in my career. I didn't start out interested in life on other planets. I've gotten more and more interested as time went on. And we don't know how common life is in the universe, right? And one of the things that life depends on here on Earth is having a certain blend of gases in the air. Well, how common is that blend, right? And how common are the planets that can host life? Right now, we know nothing about that. I think that one of the things that Webb is going to begin to teach us is how common it is to have planets with kind of our blend of atmospheric conditions.
Webb's going to be able to tell that by all kinds of things. So that's we're concluding here a little bit there. Here's another image of a tell us what that represents.
So this is a much larger scale view of the region around a black hole. And so what you can see is that you can see material streaming into the black hole, and it's forming the disk that I talked about. And the other thing that you can see that I didn't get a chance to talk about is the objects, is the black hole's jet. So that is the stream of material that you see extending out of the black hole and basically up and to the left there. And those are actually what my research specialty is. So these are streams of material that are coming out at nearly the speed of light. They are accelerated, we believe, by the magnetic fields right in the disk and of the black hole itself. And material is basically routed from those disks into the jet, and it comes out. They emit X-rays, they emit gamma rays. We see components move out in those jets. And this is one of the interesting things. One of the things that relativity does is relativity predicts things that we don't expect, right? And so you saw some of those things with gravitational lensing. One of the other things that relativity predicts is that if your geometry is right and you're looking at something that's moving at nearly the speed of light, it will actually be appearing to you as if it moves faster than the speed of light. Why? Because it's coming nearly along your line of sight. And so all the time it's moving in this direction, right? You can see its separation between the central source and whatever it is increasing, but then it's also getting closer to you at nearly the speed of light. So the distance that the light it emits covers gets shorter, right? It takes less time to get to you.
I understand that, amazingly.
Yeah.
That's interesting there. A couple other images here.
Right. And so these are obviously artists' conceptions of the
Right.
regions around black holes.
It's the speeds, the temperatures, the violence.
Right.
You just can't even comprehend it.
Right.
There again,
Yeah, exactly.
one of those jets coming out of there, in there, and
Yeah, here we go. So
we end with
one
this
of the
here.
we can end with that. That is so this is one of the most exciting things that's come out of astronomy in the last 50 years, and it really only came out in the last few years. So this is what we believe two black holes orbiting each other would look like if you were real close up to one another.
Wow.
Now, where have we found out about this? So the reason why this becomes so important is because in the last few years, we had the LIGO observatories, right? And the LIGO observatories, what they've discovered is black holes merging, okay? And black holes, why do they merge? They merge because they were orbiting each other for millions of years, right? And gravitational radiation basically makes those orbits shrink over time. And eventually they shrink so much that they coalesce into one. And what LIGO caught was that moment when they coalesced into a single black hole.
That was an incredible achievement by this, complicated to describe, but it's a worldwide network of telescopes that are tied in together, correct?
That's right.
That create
right.
this huge database. We've been talking with Eric Pearlman.
And by the way, LIGO is one of these things. So you have these citizen science projects, and I really like to give these a shout out because these are great. They actually allow citizens, people that are interested in astronomy, to participate in the research. LIGO is one of the ones where you can do this. So you can actually go over and you can find this. You can find this on the web where you can actually contribute to the work. There's far too much data that LIGO is taking in to find all of the merging black holes and merging neutron stars that are out there.
Wow.
But, citizen scientists can actually go through with their computers, and they can actually go through some of the data and then send the results back to the people that are running the observatory. And then, some of this work is actually coming out in the results that we're seeing.
Citizen scientists, are you one of them out there staying
right.
curious?
That's right.
We got Tom Usiak and Mark Usiak, two brothers that photographed over 60 shuttle launches, are watching from Lancaster, Pennsylvania. We haven't heard from Mike Gunzel in a while, Marty, in Oregon. And Ophelia is watching in Normandy, France. How about that? And we're so glad Apollo's son, Brian Morrison's probably watching in Tampa. And Chris Calais, he's a second-generation space artist. His dad was the great Paul Calais, and Chris is an awesome artist in his own. I'll bet he's watching this program here, Eric, and being entertained. Been very interesting. One final question. We love you all asking questions. Marty and I are putting together a way that maybe we can have a phone time here on Stay Curious. We were talking about, but really great to have you here and telling us about what a real astronomer is and what they do. We took I didn't even know I was going to go down that path with you, but
I think it's great.
Yeah, we really enjoyed it there. One last question: is a black hole a wormhole?
So that's a great question. And we don't know the answer to it. It could well be. That is one of the ideas, and it might be.
Marty asked that question. There's also a white hole. Could that be a black hole on the other side?
So
I mean,
again, there are ideas about that. We haven't seen one. So
when you talk about these exotic things and we don't even know what really a black hole is inside that event horizon.
That's
okay.
very true. Yeah.
It's kind of smacks of like religion, that you have to have a blind faith, right?
Well, yes and no, because now that we have the Event Horizon Telescope images of the photon ring, now that we have images of stars that are whipping around the black hole at the center of our galaxy,
Mm-hmm.
and we also have data where we literally see the position of the center of our galaxy is actually changing in position.
Oh.
And it's not because we're seeing the black hole itself. You never see the black hole itself.
Uh-huh.
But what you see is material in the accretion disk, right?
Right.
And so let's say that accretion disk has, spots that are brighter and spots that are fainter. Well, then you actually can watch its position change as it orbits the black hole. That is some of the work that the UCLA group published a few years ago. And it's a fascinating piece of work. And it was material. They actually said, okay, we know the mass of the black hole, right?
Mm-hmm.
And so from the mass of the black hole, we can work out where this material had to be if it was orbiting the black hole.
Uh-huh.
They found it was orbiting in the accretion disk at about 5 times the distance of the event horizon.
Man.
So right at the inner edge, or near the inner edge of the accretion disk. Beautiful work.
Amazing. I can follow some of this. Hope you all have been out there with our Stay Curious fans out there. Marty, you got something else?
Yeah, 2 things. First, Larry Puskar said, "This is one of your best shows. Thanks."
Oh, well, thank you, Larry.
And then
Thank you, Larry.
Yeah.
Keith Starrell, okay? It's a long one. A black hole is a misnomer. There ain't no hole, but actually a solid body of what I call negative energy, which sucks up the positive energy and burps what's left outward.
Well, that's an astronomer talking back to you there.
And that's an interesting idea. And I want to know how to test that. I got to think about that one.
Okay. All right. Well, we thank Keith out there. He's always got some good points to make out there. Tom Celentano, hope you're watching. Diane George is another one that watches our show a lot. And Connie McDaniel, we haven't seen you in a while, Connie. Hope you're doing well, one of our ace volunteers here at the museum. So thank you all for watching this. The time went by fast. We will see more of you, Eric Pearlman. Thank you very much, sir.
Thank you.
You did a tremendous job. I think our Stay Curious people will want you back to kind of balance my amateur stuff with your professional stuff there.
Well, thank you. And let me just tell you one of the things that one of the things I love about astronomy is that every day, every week brings something new that I didn't understand and I didn't expect. So one of the things that got published a couple weeks ago, that I showed you this picture. I'm sorry it didn't make it into our slide deck, but I'll tell you and our
next
viewers
show we'll
about
have it here for sure.
I'll tell you and your viewers about it now. This is a paper that just came out about 10 days ago. What this paper has is it has the first observations of a supernova and the star in the year before it went supernova.
Ooh.
So, the question is, okay, star's going to go supernova. What happened to it in that year, right? And we know in that year, it's building up that iron core that's going to collapse, and the collapse is going to generate the shock wave that's going to cause the supernova. Well, what happened to it? Well, what happened to it is that starting about 130 days before the supernova, it got brighter. it increased in brightness by about 50%.
Mm-hmm.
And then it stayed at about a constant luminosity, and then the supernova happened.
Mm-hmm.
Now, what else was going on? We don't know. We don't have spectra. We don't have any other observations. So this is just the first of probably a whole bunch of these that we're going to find, because we have the LSST that's going to be opening up next year, right? And one of the things that the LSST is going to be doing is it's going to be monitoring basically the entire southern sky every night. And so it's going to catch a whole bunch of these, right?
Mm-hmm.
And so this is not the only one we're going to see. This is just the first time we're seeing it. We're going to see a whole
actual
train
star
of them.
exploding,
right,
in a timeline that we can understand.
Exactly. And the reason we could see this, by the way, is because it was in a galaxy fairly near to our own, about 35 million parsecs, or about 110 million light years away.
And that is in our neighborhood
So,
here. Well, thank you. We'll pick up on that next time we have
Absolutely.
Eric Pearlman back here to help you all stay curious. Thanks again. I'm glad you all enjoyed the program. I certainly did. You had a great way of making it sound simple to all of us, I think. Appreciate that, Eric. So we will have you back soon. Maybe get a date down where we can have you in once a month or so to talk about some of the real science going on with the Webb. Marty?
Just real quick. Heath South said, different camps, string or bubble.
Okay. String theory or bubble theory? Yeah.
Not
Gotcha.
sure,
Gotcha.
actually.
Yeah. Well, that's what the beautiful thing about astronomy is you can agree to disagree.
That's exactly right.
Because no
That's
one
exactly
knows the
right.
exact thing until you get all the data in. But thank you for enlightening us all about your career as an astronomer, working with the beautiful the Hubble Telescope. And we'd love to have you back. So
Great.
And you really did a good job. Marty, we'll be doing it again tomorrow for all of our Stay Curious listeners. We got to catch up on 4 or 5 astronaut birthdays and some other things that's going on in space history. And I'll be happy to do that next week or tomorrow and the rest of the week. Thank you, Marty, for what you did. Jessica was in the background there earlier in the show. And all of our staff here at the American Space Museum. Eric, we're so glad you're here and can't wait for you to come back again to what? Bridge the space between us.
Absolutely.
We'll see y'all again.